Section 5.4, Working with Integrals. In this section, we're going to pick up a couple of miscellaneous topics involving definite integrals. The first one has to do with integrating even and odd functions. So just a reminder, an even function satisfies the property that f of negative x is equal to f of x. So if you were to substitute a negative x in place of the x and simplify, you get back to where you started. And what's special about an even function is it's symmetric about the y-axis. So the y-axis over here is the axis of symmetry, and you have this mirror image thing going on the left and the right. So we end up getting a special case with even functions if we're doing a definite integral and our limits of integration are the same but opposite sign numbers. So if we're going from negative a to a, we refer to those as symmetric limits of integration because they're equal distances on either side of the y-axis. So what happens if we're doing an integral from negative a to a of an even function with respect to x? Well, let's think about splitting it into two cases, from negative a to 0, so the left-hand side, and then from 0 to a, and think about what happens with those. So here's the left-hand side. You're finding this area right here, this region. But because of the symmetry, that's exactly the same as what's going on the other side. So the way we take advantage of that is we can just do one integral and multiply it by 2. And we'll do the integral from 0 to a of f of x dx. So with an even function and symmetric bounds, you can just find the area on the right-hand side, and because you know that's equal to the area on the left-hand side, you can just multiply that by 2 and get your answer that way. And it's a little easier to do that often because 0 is often an easy number to plug in and simplify, whereas that negative a number might be messier. So just a reminder of some functions that are even. For the trig functions, you've got f of x equals cosine of x is an even function. If you're dealing with a polynomial, then something where all the terms are even power, so something like 3x to the 8th minus 5x to the 4th plus 6. So a constant term is considered even. So notice we've got the even exponents there, the 8 and the 4. And then the 6 is considered a 0-degree term because it's a constant. It doesn't matter that you have odd coefficients. It's about the exponents. And again, a constant term is like 6 times x to the 0, so that's considered an even term. So both of those are examples of even functions. The even better trick comes out of working with an odd function. So just a reminder of what it means for a function to be odd. That would be one that satisfies f of negative x equals the negative of f of x. So an odd function is one where you plug in a negative x in place of x, you simplify, and if you factor out a negative, then once that negative's out of the way, you're left with what you started with. And what's special about odd functions is they're symmetric about the origin, which means that if you take a point somewhere on the graph, and then from that point you draw a line through the origin, then it'll go back onto the graph like an equal distance away on the other side. So that's what symmetry about the origin looks like. And now let's suppose we had symmetric bounds like we were talking about for the even function, so that we were going from negative a to a. And we split it up into the two cases again, the left side and the right-hand side. Well, once again, by the symmetry, the area on the left will be the same size as the area on the right. But what's different about it this time is the area that's above the x-axis will be positive, and the area below the x-axis will be negative. So they will be equal but opposite areas, and so on this one, we get a much better answer. We just get an instant 0 there. So for an odd function, you don't have to find the antiderivative. You don't have to plug in any numbers. If you have those symmetric boundaries, you just know you're going to have that 0 answer. So this one's more important to recognize than the one where you're working with an even function. The even function thing is nice. The odd function thing is great. So we need to make sure we recognize that one. So what do odd functions look like? Well, in the trig family, we have sine of x and tangent of x are both even. So that's your main three. Of course, the other ones fall into odd and even categories too, but you can just think about how they relate to these. So, for example, secant is the reciprocal of cosine. So since cosine is even, so is secant. So you can kind of get to the other ones that way. And then as far as polynomials go, you would need all of your terms to have an odd degree. So something like 8x to the 7th minus 5x to the 3rd plus 4x. Again, coefficients don't matter, so it doesn't matter that we have some even coefficients. It's about the exponents, odd, and odd there too, because if you have x, that would be x to the 1. All right, so let's go ahead and look at an example, and we'll take advantage of this as much as we can. So let's use symmetry to evaluate the following integrals, starting with the integral from -5 to 5 of x squared minus 7x cubed. So just looking at a few things as we get started. First of all, we have those symmetric boundaries. That's key. And then we look at it and we think, all right, is this one odd or even? And we have a problem right away. We have an even exponent at an odd one. So it doesn't seem to be either of those. It's neither of those. So it seems like, well, I'm not going to be able to use these properties because I don't have an odd function or an even one. But remember, we can split these up. So we could rewrite this as the integral from -5 to 5 of x squared dx minus the integral from -5 to 5 of 7x cubed dx. So now what happens is we've got an odd case and an even case, and so we can use both of these properties on the same problem. So for the first one, that's where I've got the even. So I've got that x squared right there as my only exponent is an even term. So I can make this one 2 times the integral from 0 to 5 of x squared dx. And again, that'll just be a little bit easier to evaluate than going from -5 to 5. But the really big thing is this next one is odd, and we have the symmetric bounds. And so the answer to that piece is just 0. So that's great. Now that's a part we don't have to really work with at all. So continuing on, 2 times the antiderivative of x squared, which would be x to the 3rd over 3, evaluated from 0 to 5. So we plug that 5 in. We get 2 times 5 to the 3rd over 3, and then we just have a minus 0. And then 5 to the 3rd is 125. 2 times that would be 250. So we end up with 250 over 3. So that actually is a decent time saver if you recognize that you can split this up with the odd and even terms separate. Use the 0, which made a nice easy plug-in for the limits of integration. That 0 made this 0 happen. And then the fact that this one was odd made that 0 happen. So a lot of our work kind of vanished away from us, and we ended up with a pretty easy problem because we recognized that we could break it into odd and even pieces, but more importantly, because we had symmetric boundaries. You can only do this and really take advantage of it if you have the symmetry, and symmetric boundaries are always going to create that symmetry for odd or even functions. All right, we'll look at some more examples. All right, next example, we're taking the definite integral from -π/4 to π/4. You want that to start catching your attention right when you see that we have symmetric bounds on our integral. We have symmetric limits of integration. So when you see that, you should immediately start thinking about, do I have odd and even parts? Can I break it into pieces? Can I take advantage of that? And we can. So let's go ahead and break this into 2 pieces. The first one will be the integral from -π/4 to π/4 of sine cubed of x. And then we'll do another one for the integral from -π/4 to -π/4 to π/4 of cosine of x dx. So just a reminder, the sine of x falls into the odd function category. And if you take something that's odd and then raise it to an odd power, it will still be odd. So this whole piece right here is odd. And then we have symmetric limits of integration. So that's the awesome one. That's the one that just becomes 0 right away. On the next one, we have cosine, which is an even function, and we have the symmetric bounds, so not as great, but we can change it to 2 times the integral from 0 to pi over 4. Sorry, that is a terrible little 0. Let me fix that up. And then of cosine of x dx. And now we've got kind of a simple thing to work on. The 0 we don't have to worry about. We've got the 2 out front. Cosine is the derivative of sine, so the antiderivative of cosine is sine. And then we're going to evaluate that from 0 to pi over 4. So we get 2 times the sine of pi over 4 minus the sine of 0. Sine of pi over 2 is root 2 over 2, so we get 2 times root 2 over 2. Sine of 0 is 0, so I guess we could put the parentheses there for now. And then the 0 is going to go away, the 2's are going to cancel, and we just end up with a nice clean root 2 for this one. Worth mentioning, by the way, that at this point in our calculus careers, we don't know the antiderivative of sine cubed of x, so we wouldn't have known how to find that antiderivative. So that's like some really high-powered stuff here. We were able to find the value of this definite integral even though we didn't know the antiderivative to one of the pieces. And we could only do that because it was an odd function with symmetric bounds, and so even without knowing the antiderivative, we know the answer to that piece is 0. So again, that's pretty powerful. So it's good that we could take advantage of that, make this a much simpler problem. All right, next example. No symmetric bounds, right? We're looking at the integral from 0 to 10 of the absolute value of x minus 5. And yet it still says use symmetry to evaluate. So let's think about where the symmetry is and how we could take advantage of that. Let's start off by thinking about a simpler version of this function, which would be y equals the absolute value of x. So if we were to graph that one, that's kind of a V shape. And it is, if you look at it, symmetric about the y-axis. So we do have some symmetry right here, but we don't have the symmetric bounds, and that's not actually our function, right? So what actually is our function? Our function is y equals the square root of, the absolute value of x minus 5. So what does that minus 5 do? Well, where was the kind of sharp point on our v? It was when the inside part was equal to 0. So when is the inside piece here equal to 0? That would be when x equals 5. So what happens is this graph just gets moved over 5 units, still has that V shape, just slid over. But the symmetry is there. The symmetry now, though, is about the line y equals 5. So if we tried to find the area under the left-hand side from 0 to 10, and I'll just highlight a little part of it right here, and then area on the right, they would be the same. So we could just do a doubling. So what I'm going to do here is say this is 2 times the integral from 5 to 10 of the absolute value of x minus 5 with respect to x. So I guess I could do the integral from 0 to 5 instead and still double it because the area on the left and right hand side of the axis of symmetry is the same. So as long as we're splitting it in half, we could do either one. There is a benefit to using the right hand side, which I will show you right here. What does y equal to the absolute value of x minus 5 look like? Well, it's actually a piecewise function. What does absolute value do to what's inside it? It leaves it alone if what was inside of it was greater than or equal to 0, and it changes its sign if what was inside of it was less than 0. So if you take this x minus 5 is greater than or equal to 0 piece, and you add 5 to both sides, you see that the splitting point is that x is greater than or equal to 5 versus x is less than 5. And so since we're only looking at the integral from 5 to 10, all of that's going to fall into this case where x is greater than or equal to 5. So during that whole window, our function looks like x minus 5 without the absolute value. So by splitting it into two pieces, we're not dealing with the two branches of the function anymore, right? Because the function has these two different branches. We've got the x minus 5, but we also have the negative of x minus 5. But you only have to deal with both of those branches if you're covering both of those parts of the domain. By using symmetry here and just going from 5 to 10, I only have to deal with this side and therefore that branch. So this ends up becoming just 2 times the integral from 5 to 10 of just x minus 5, no more absolute value. And then it's easy to take the antiderivative. We get x squared over 2 minus 5x, and a little messy perhaps to evaluate, but we're just going to go from 5 to 10. So kind of make some space here, and let's just keep working. So we have 2 times, we plug in the 10, we get 10 squared over 2 minus 5 times 10. And then minus what we get when we plug in the 5. The 2 applies to all of it, so I'll put brackets right there. So plugging the 5 in there, we get 5 squared over 2 minus 5 times 5. And just to kind of talk through the simplification, and then I'll write down the answer. Let's look at some of these pieces. There's kind of some nice stuff that happens. 10 squared over 2 is 100 over 2, which is 50. This is also 50. So all of that just goes away, cancels each other out. And then if we look over on the other side, 5 squared is 25 over 2, so that's 25 over 2. This is 25 over, or just 25. So right here we have 25, right here we have half of 25. So when you take 25 and subtract half of 25, you get the other half of 25. You can do the common denominator work too, but this part right here ends up being the negative of 25 over 2. And then we have the double negatives. So we just end up with 25 over 2. So we were really only able to find this integral by thinking about the piecewise defined portion. Otherwise, these absolute values were going to kind of block us from taking an antiderivative. We don't have any rules about how to take an antiderivative when there's absolute value. So if you go to this piecewise definition of the function over here on the right, that gets rid of the absolute value. But if we were working from 0 to 10, the function is defined differently over different pieces. So I could break it into 2 pieces and use both of the different branches, or I can take advantage of symmetry and just use one branch and do times 2, which is what we ended up opting for. And speaking of that times 2, looks like I forgot it. So we were supposed to have a 2 times out front, 2 times out front. That 2 is going to cancel this 2, going to cancel that 2. So we're actually not getting 25 over 2. We're just getting 25. So let's clean that up. There we go. All right, so that wraps that one up. Let's go ahead and have a look at another. So in this one, they want us to look at the integral from 0 to 2 pi of sine of x. So again, what we want to see right away is we don't have symmetric bounds. We don't have negative pi to pi. We don't have negative 2 pi to 2 pi. So how does symmetry come into play on this one? Well, let's think about the graph of sine. So a sine function starts out at 0. When you get to pi, it's 0 again. And when you get to 2 pi, it's 0 again. When you get in between at pi over 2, sine is up to 1. When you get in between over here at 3 pi over 2, sine drops down to negative 1. And in between, you have that sine wave that we learned in trig. But if you look at it, what's going on there? Something pretty cool is going on there. This portion and this portion are equal but opposites. And in fact, that's kind of why sine can end up being an odd function because it does the same thing. If you went over here to negative pi, you get another branch of that. And this one right here cancels out this one right there. And that's what would happen with the symmetric bounds, but it can still happen where these two cancel each other out as well. So we could go through all of the work, but if we notice that symmetry, we could just say right away that this is going to be 0. So there it is just from looking at it. Let's go ahead and do the work too, just to get some practice with definite integrals. What's the antiderivative of sine? Negative cosine. And then you would evaluate that from 0 to 2 pi. You can take the negative out front, plug in cosine of 2 pi minus cosine of 0. You can have that negative out front. What is the cosine of 2 pi? So do a tiny bit of unit circle work over here. 2 pi is right here. Cosine is 1 in that spot. What about cosine of 0? That's the same spot. 2 pi's is making a full circle before you get there, but they're both the same kind of terminal angle. So cosine of 0 is also 1. The two negative ones, or the 1 and the negative 1 cancel. We get negative 0, or just 0. So if we spot the symmetry, we get our answer essentially with no work. We just realize there's going to be a region up top that cancels a region on the bottom and just go to the 0. If we didn't notice that, this is what the work looks like. We still get 0, and the work's not that bad. All right, our next topic is the average value of a function. So consider a function f that is continuous over a closed interval from a to b, and we suppose we want to know the average value of that function. Let's just kind of look at a generic graph of such a thing. So let's suppose this was our graph going from a to b, and we wanted to know the average height of that function. Then we could chop up the function into a few intervals. In this case, I'm doing 4 of them. We could find a value of the function in each of those sections by plugging into it. And we could then add those together and divide by the number of values. So traditional average, right? If you want to know the average height and you had 4 heights, add the 4 heights and divide by 4. So what we're looking at over here on the left is the same idea, but instead of breaking it up into just 4, we're going to break it up into n sections. So in each one of those sections, you'd figure out the height. So what's the height of a function? You take an x value and you plug it in and you get the height. Then do another one and keep doing that till you get all the way to the last one. There would be n heights, and the average would then come from dividing by n. If you did that, you would still just be approximating the average value of the function because you're not actually averaging all the heights, but just n of the heights out of infinitely many. So somehow we want to take the limit as n goes to infinity and have a way of evaluating this average of infinitely many points. So one of the keys to helping us do that is to realize that n is equal to b minus a over delta x. So where does that come from? Well, what is our formula for delta x? Delta x, when we were doing Riemann sums, we said delta x was b minus a over n. Okay. But then what if you multiplied both sides by n and divided both sides by delta x? Then these n's would cancel, these delta x's would cancel, and you would get n equals b minus a over delta x, which is what they've got for us right there. So in this next line below, they're rewriting this, but instead of writing m in the denominator, they're making the substitution b minus a over delta x. So that substitution is happening right here. That used to be n up here, but now they've substituted b minus a over delta x. That delta x in the denominator, though, can get pushed up into the numerator. So if we do that, what do we get? We end up with the same numerator, f of x1 plus f of x2, all the way out until we get to the nth one. And then we could still have the b minus a in the denominator. And the delta x, if we push it to the numerator, we could also push it off to the right-hand side. And that's where we usually have the delta x when we start thinking about Riemann sums. So now, taking this and making a Riemann sum out of it, we could take the b minus a in the denominator, move that out front as 1 over b minus a because it's just a constant. And then for our numerator, we could use summation notation to represent that piece. So we could write the sum as k goes from 1 to n of f of x sub k times delta x. And hopefully you're starting to recognize that this looks a little bit like the Riemann sums that we turned into definite integrals before. So if we wanted to get a true f average, and we do f with a bar over the top of it. If you've ever taken statistics, x bar is what we often use for an average x value. So for the average value of f, we'll write f with a bar over it, or f bar. And what would that be? We could still have the 1 over b minus a out front, and then we could take the limit as n goes to infinity of the sum as k goes from 1 to n of f of x sub k times delta x. And that's the sort of thing that we turned into an integral before. And we're going to do that right now. So what happens? The limit of the sum becomes our integral symbol. So let's go ahead and write that below. We'd have the 1 over b minus a out front. And then the part I just highlighted in yellow becomes our integral over the interval. So that would be from a to b. And then the next piece is our function, f of x sub k. That part becomes our f of x, and the delta x becomes dx. So there's how we get to the average value of a function through integration rather than an average of infinitely many points. So the average value of a function, let f of x be a function that is integrable on the interval from a to b. Then the average value f bar of f of x over the interval from a to b is given by f bar equals 1 over b minus a times the definite integral from a to b of f of x with respect to x. So there is our formula for the average value of a function. F bar equals 1 over b minus a times the definite integral from a to b of f of x dx. All right, so down here we have an illustration of what's going on. We have all these different heights on our function. There's infinitely many different heights, but the average value f bar represents kind of, if you were to somehow take all infinitely many of those points and average them, what would the height be? Another kind of interesting thing that comes out of that is if you take the formula that I've highlighted in green up there, and then you multiply both sides by b minus a, you would get that f bar times b minus a is equal to the definite integral from a to b of f of x dx. So what's kind of interesting about that in the picture, we know that this integral from a to b of f of x dx represents the area under the curve. So that's kind of all of this piece. But this part over here, what does that represent? It's the average height times the width of the interval. So that actually just represents this one rectangle. So we've talked about the area before as being the sum of all these rectangles as the limit of the number of rectangles goes to infinity. If you could somehow know the average height of the function, you could actually perfectly approximate the area under the curve using just one rectangle. And that rectangle would be one that had the average height of the function over the interval. That sounds like it's going to be some great trick to make it easier to do definite integrals. It's not really. It's just an interesting side point, because in order to know the average height of the function, you have to take the definite integral. So you kind of get caught in a loop there. There's no real shortcut, but just kind of interesting that when you find the average, you're finding a height that has one single rectangle that equals the messy area underneath the curve. All right, let's look at the kind of examples that we see that involve average height or the average value of a function. So suppose the elevation of a path is given by f of x equals x cubed minus 5x squared plus 30, where x measures horizontal distance. Find its average value from 0 to 4. And that path is shown over here on the right. So we're walking along this path, starting off, it looks like, at an elevation of 30, and then we drop downhill, we reach a low point, and we start walking back uphill a little bit. So we have all these different heights along the way. We've got our starting height, we've got a height here, height here, height here. We could find all these individual heights by plugging in their x values into the function. We could add them all together and divide by the number of values and get an approximation of the average height. That's straightforward enough to do, but it's awfully tedious to plug all those different values into the function. They would each produce messy heights, then add all those messy heights together, and then do a division. Much better to use this formula up here for f bar equals. So that's what we're going to do. If you want the average value of the function, that's f bar. F bar will be equal to 1 over the length of the interval, which is 1 over b minus a, so 1 over 4 minus 0. You do the definite integral from 0 to 4 of the function. And our function is just a polynomial. So finding the antiderivative will be straightforward. Plugging in will be maybe a little messy, but we'll survive. So we have 1/4 out front. We have our antiderivative would be x to the 4th over 4 minus 5x cubed over 3 plus 30x. And then we would evaluate that from 0 to 4. The 0 will be nice and easy to plug in. It'll just produce a 0. The 4 will be a little bit messy. So we have the 1/4 out front. We have 4 to the 4th over 4 minus 4 to the 3rd over 3 plus 30 times 4. Then we would have the minus that we get when we plug the 0 in, but when you plug the 0 in, you just get a 0. So that part right there, that's what we need to figure out. I'm going to go ahead and show you the little trick I did before on the calculator, and we're just going to let the calculator sort all this out and convert it to a fraction for us. So let's head there. So I'm just going to type that in. I have the 1/4 times. I like to do a times there before the parentheses, though that's not really necessary. And then we have 4 raised to the 4th divided by 4. And then minus 5 times 4 raised to the 3rd divided by 3 plus 30 times 4. So when we press enter, we get something a little messy. But the trick I showed you before, if we go into the math menu over here on the left below the alpha key, then we can convert that to a fraction as the top choice. And we press enter and we get 58/3. So let's go back, write that answer down. Equals 58/3. So there's our exact answer. Of course, if they wanted us to give a decimal, then we could go ahead and round that to as many decimal places as they want. But for now, we'll have the exact answer until we have a request for something else. All right, on to the next one. All right, in previous sections, we had something called the mean value theorem. Now we're going to look at the mean value theorem for integrals. So let f be a continuous function on the closed interval from a to b. Then there exists a point c somewhere in that closed interval from a to b such that f of c is equal to the average value of the function, which we said on the previous page is 1 over b minus a times the integral from a to b of f of t dt. So at some point, the function will equal its average value if f of x is continuous. So we talked about finding the average value of the function. It's possible, like if you have the average value on a test that we take, maybe nobody scored that average value. But they're saying that for the mean value theorem of integrals, as long as your function was continuous, then the average will be achieved at some point on the function in the interval. So let's go ahead and look at an example that explores that idea. So find the points on the interval from 0 to 2 at which f of x equal to x times 2 minus x equals its average value on 0 to 2. So the first thing to do is to find the average value. So we're going to go ahead and look for that. So f bar would be equal to 1 over b minus a, which would be 2 minus 0 in this case, times the integral from 0 to 2 of the function in question. In this case, that's x times 2 minus x with respect to x. So up here, by the way, they used a t, but I mentioned this before, we call that a dummy variable in a definite integral. The definite integral comes out the same regardless of what variable we use. So we could match their t if we want, but we might as well just match what was given to us here, which is the f of x equals. All right, so we want to go ahead and try and evaluate the integral so we know what the average value is. So we have that 1 over 2 out front. We're doing the definite integral from 0 to 2. We need to get rid of this product because we don't have a product rule for integrals. So distribute, and we get 2x minus x squared. Now we just have a polynomial, so we can do the antiderivative fairly easily. We just do the antiderivative of 2x, which would be x squared, and the antiderivative of x squared, which would be x cubed over 3. And then we're going to evaluate that from 0 to 2. Plugging in the 0 will be easy. Plugging in the 2 may be a little bit messy. So we have the 1/2 out front. We get 2 squared minus 2 cubed over 3 minus what you get if you plug in the 0, which for a polynomial ends up being 0. And if you simplify all of this, I'm going to go ahead and breeze through the math. It just becomes 2/3. So get your common denominators, all that fun stuff. You end up with 2/3 for this one. All right, so now part 2, we found the value of the function. They said find the points on the interval from 0 to 2 where the function takes on its average, because that is what's being claimed by the mean value theorem. Our function here is a polynomial, so it is continuous, so it should achieve its average somewhere between 0 and 2. They're asking us to find those spots. This is a pure algebra task now. Take that average value, 2/3, set that equal to the original function, which was the x times 2 minus x. Now just use algebra to solve. So clearing the parentheses, we have 2x minus x squared. We bring the 2/3 over, and then we could set it equal to 0. This is quadratic. I'm going to multiply both sides by -3. That may seem a little bit of a strange value to pick. But if I multiply both sides by -3, that will accomplish two things. It'll make the squared term become positive when I multiply by the negative, and it will also get rid of this denominator right there. So we'll go ahead and do the distributive property. So -3 times 2x is -6x. And then -3 times -x squared is positive 3x squared. When we do the last multiplication right here, the two negatives make a positive, the 3's cancel, and we just get the 2 equal to 0. Just putting this in descending order, we have 3x squared minus 6x plus 2. All right, so we need to solve that somehow. Quadratic formula is an option. So if you want to use quadratic formula, your a is 3, your b is -6, your c is 2, go for it. But whenever you have an even for b, the quadratic formula always ends up having a lot of simplification to do. So instead of using the quadratic formula, and I forgot the equals 0 over here, but instead of the quadratic formula, I'm going to use completing the square instead. So I multiplied by 3 to get rid of fractions. Now I'm going to backtrack on that a little bit. I'm going to divide everything by 3, because when you complete the square, you want it to just be 1x squared. If you were going to use the quadratic formula, the multiplying by 3 that I did would be very useful, because then you don't have fractions in your quadratic formula. But if you're going to complete the square, you need the lead coefficient to be a 1. And then I would have -2x, and then I have plus 2/3, but when you're completing the square, you take the constant term and you move it to the other side. And then you take this number that's in front of the x after you've got a 1 as your coefficient on x squared. you take that number and you divide it by 2 and square it. So I'm going off to the side over here. Negative 2 divided by 2 squared is going to be a 1. If I add 1 to both sides, the left side should be a perfect square. And if you factor it, you'll see that's true. What are two numbers that multiply to 1 and add up to negative 2? Negative 1 and negative 1. So the left side is x minus 1 twice, or x minus 1 squared. And on the other side, I think we just have 1/3. And then you can take the square root of both sides. So the square root and the square cancel. And we get x minus 1 equals plus or minus 1 over root 3. It's really the square root of the whole thing, but the square root of 1 is 1, so I simplified that. And then we can just add 1 to both sides, and we get x equals 1 plus or minus 1 over root 3. So I think that's our answer. The one part that's messy about that is I'm supposed to find the places where the function is equal to its average value over the interval from 0 to 2. And this is a little bit of a messy thing, so it might not be obvious at first if this is between 0 or 2. We can do a little bit of logic on it, I suppose. Square root of 3 is bigger than 1, so 1 over the square root of 3 is smaller than 1. So we're taking 1 and adding and subtracting something that is smaller than 1. So when you take 1 minus smaller than 1, you'll be bigger than 0. And 1 plus smaller than 1 will be smaller than 2. So you could check that on your calculator if you want, but I just convinced myself that both of those are between 0 and 2. Hopefully I drug some of you along with me as I talk through that. But again, feel free to put it into your calculator to verify that both of those numbers are between 0 and 2, but they are, and that's what they asked us to find. What are the two x values that make the function take on its average value? So 1 plus 1 over root 3 and 1 minus 1 over root 3 are those two values. All right, that wraps up section 5.4.